Okay, excellent. And yeah, if you can.
Start at the first slide.
Oh, yeah.
Not the last.
There we go. Okay, and yep, so we've got forward, back. This takes a minute to pop up. Okay. All right, great. Looking forward to hearing from Miles Lucas on another interesting disk system.
Hi, everyone. Thanks for being here. Thanks for your attention and focus. I'm Miles. I'm a postdoc at the University of Arizona working on high contrast polarimetric instrumentation. Today, I'm going to discuss some work I finished for my dissertation and published last year, doing an analysis over a bunch of data sets using high contrast polarimetric images. So let me introduce you to our target of interest today. This is HD 169142. Up here in the top right, this is the thermal emission image of this data. And when I say thermal, I mean millimeter continuum emission. So this is the thermal emission from pebbles and small rocks that have fallen into the midplane and towards the star. And we can image that with ALMA. In the bottom right here, I have a scattered light images. So this is tracing the gas atmosphere a lot more via reflections of starlight off submicron size grains that are suspended in the atmosphere. And the two of them together give kind of a complementary view, a view of the solids and a view of the gases. As we look at this disk, you can see there's a lot of very interesting features, and that's why we're excited about it, because disks should not have all of these different features. As we go through, I've got this schematic in the middle that we're talking about, and on the bottom, these are also radial profiles of the disk that you can refer to. So right in the middle, we have the star itself. It's a Herbig star. It's young, 7-ish megayear, and it's more massive than solar mass, so 1.9 solar mass. Around this disk is a Gaussian envelope, a shell of dust that has been measured with gravity. Beyond that is a cavity which has been cleared of material as far as we can tell. Then we have an inner ring, a large annular gap, and an outer ring. And in that outer ring, in the scattered light, we see a broad diffuse structure. And in the midplane, the millimeter emission, we see 3 rings with gaps, and those rings that are actually eccentric. This disk is very exciting. There's been a candidate protoplanet reported here in that annular gap. In the top right, we're looking at ASDI residuals from SPHERE, where that blob in the top left of that plot has been resolved in multiple epochs of SPHERE data, and that blob is moving with Keplerian velocity. So this is potentially a forming protoplanet. Beyond the imaging data, there's also information from molecular line mapping from ALMA that shows both an excess of kinematic pressure in that gap, as well as volatiles that are not expected to be in the disk, potentially pushing towards information of a circumplanetary disk. In addition, in that inner ring, there's a lot of non-axis symmetric brightness variations, and there was a previous paper done with some SPHERE data that hypothesized that these brightness variations could be caused by a companion interior to the ring, wherein this shadow feature appears to be moving faster than the Keplerian velocity, meaning it's not driven at the same radius. This is really the onus for the study that I'm doing, which is the idea that we can take just images of disks over time and analyze them dynamically to learn more about potential companions within this disk and form hypotheses about the planet-disk interactions. So when we're talking about the dynamics, we have to talk about the null hypothesis here, which is just normal Keplerian velocity. So any particle within the disk is going to act just like a particle around the star. So it depends on the stellar mass, and it depends on its separation from the star. We can encode this information into an image transformation, which is something that I'll be playing with a lot here. What that lets me do is take a single image, and here in 2D space, it's kind of swirling it around to any given time. So the inner pixels are rotating faster than the outer pixels, just like the particles in the disk. For context, this disk, since it's 1.9 solar mass, at the location of this inner ring, we're looking at about 5 degrees of expected motion per year. And that's what enables this study, is a lot of motion that we can resolve over a multi-year baseline. This is the suite of archival data that I've been looking at. So it goes back to 2012 NACO data, which has been reprocessed with the Pippin pipeline. We have some GPy data, SPHERE, both IRDIS and ZIMPOL. Those are all archival, and then the 2 Skexeo data here from Keras and Vampires were additional, were new observations provided for this disk. Here in the broad view, they share a similar morphology. You have an inner cavity, inner ring, annular gap, and then a broad diffuse outer ring. And we see that pretty equivalently across different instruments, different years, and different wavelengths. When we zoom into that inner ring, we start to see some of those non-axisymmetric brightness variations a little bit better. You can see, for example, here, I always look at the GPI data. You can see like a clump there, that clump's in the Irdis data, and you can see in the Zimpol data. And what I'm going to do is take this, and I'm going to unroll all of these plots of the inner ring into polar coordinates. And now I think we can really start to emphasize those features. I put a little key up in the top for the features I'm referring to. I call them clumps and shadows, which is kind of poor terminology, but those are just more bright features and less bright features. So there's kind of this clump, then a shadow, clump, a larger shadow, another clump, and then this outward bowing where the ring itself is not circular or elliptical within the disk. And if you look in polar coordinates, you can see these features you can see the motion of these features a little bit more clearly. Now, I showed you earlier how we can encode Keplerian motion into an image transformation and play with our data that way. So what I'm going to do is take all of these images, and I'm going to shift them into a common Keplerian reference frame. Okay, so I've interpolated them all to a single point in time. What this means is that anything that appears constant across all of these data are moving with Keplerian velocity. And to me, what I see is those features, the clumps, the shadows, and this outward bowing, appear static in this reference frame, implying that they're moving with Keplerian velocity. I like this because this is a good qualitative analysis that we can see our data moving, and it's moving at a velocity that we expect. But we need to do a quantitative analysis to be able to make meaningful conclusions and do science. To do that, I'm going to use phase cross-correlation. So this is a technique that lets us take data and analyze the shifts in any dimension by looking at the Fourier phase of it. So given two signals, the correlogram that I'll be calling, the phase correlogram, the location of the peak is the shift of the signal, and the shape of the peak is the correlation between the two signals. And what I'll be applying that to are these azimuthal profiles of both the inner ring and the outer ring. So I take two azimuthal profiles from a pair of data, and when I cross-correlate them together, I get this curve. So this curve has a peak that's giving me the shift of these signals in degrees. I can then divide by the time between the two observations and get the angular velocity in degrees per year. And what we can see here is, again, the peak is essentially the measured velocity, and the amplitude and shape of that peak is telling us how correlated the two signals are. If they're more correlated, you'll get a thinner, higher amplitude peak. For all 27 combinations of pairs of data, I created these phase correlograms and angular velocity, and I've averaged them together for both the inner and the outer ring. I'm showing here in a solid line the measured peak for my analysis, and I'm getting error bars using bootstrap resampling. And the dashed line is showing the expected angular velocity from Keplerian motion at the location of these rings. These values are also plotted in the table. And first off, we can see that the inner ring has significant Keplerian motion, or has significant motion at something like a 6 sigma level, and that motion is really well explained by the Keplerian motion at like 0.05 sigma. So the inner ring quantitatively also looks like it's moving with Keplerian velocity. And we can start to make interesting conclusions for that. So, for example, those brightness variations in the inner ring are not from shadows casted by an inner companion. So that whole hypothesis is kind of ruled out from this analysis. We can also, when we look at the outer ring, the results are a little less conclusive. I've got wider error bars on this motion, so it's not really conclusive yet whether the outer ring is moving with Keplerian velocity or isn't moving at all, and both of those are plausible explanations. When we look at the companion, an interesting idea is that a companion can create spiral waves inside of our disk, and those spiral waves should move at the same angular velocity as the companion. So we can further use this data and show that, in this paper, there's a claim that potentially this feature is a spiral wake from this candidate protoplanet, but because the outer ring does not show approximately -2 degrees of motion at a 2.2 sigma level, that's not a good explanation for this feature. I think a better explanation for this feature is that we're just seeing ADI residuals in the data. It's not moving fast enough to be a spiral wake. It's also not gravitational instability because the disk isn't massive enough. And furthermore, when we look at hydrodynamic simulations of spirals caused by Jovian mass companions, they're really bright in both, or they're really visible and bright in both the continuum and the scattered light, and they're really, I don't see any spirals here. So spirals aren't a good explanation for anything in this disk. What I'm most interested in, to give you a future hypothesis to be able to test, is these brightness variations are very interesting to look at both the millimeter and the scattered light. When we look at this animation in the bottom right, I feel like the millimeter emission and the scatter light are kind of piecing together like puzzle pieces. This dirt, this shadow here, is almost perfectly kind of carved out by this tendril feature. And you can see similarly, these tendrils from the millimeter emission are kind of carving out the disk itself. And this outward bowing is where in the millimeter emission you don't really have any tendrils. So what this is telling me is that there's some kind of pressure trap that is segregating the large grains that we see in the millimeter emission from the small grains that we're seeing in the scattered light. Now, as to why we have non-axisymmetry, there's some estimates of the water-ice transition region, and that is right in the middle of this disk. So potentially what could be happening is that we have differential evolution of dust near this snow line, where you can get coagulation and drifts, that are causing this non-axisymmetry in addition to this pressure trap. So you have kind of a leaky pressure trap with differential evolution over a snow line. So in conclusion, I've taken this suite of archival and new data, all polarimetric of the HE169142 disk, and shown via dynamical analysis that the features of the inner ring are not being cast by inner companion, nor are they related to spirals or the HE169142b protoplanet candidate, and same with the outer ring. I show that there are some interesting correlations between the millimeter and the scattered light, in the inner ring. Also, this is just a good example of why we should keep taking polarimetric images of disks, because it enables these multi-wavelength, multi-epoch analyses. So keep acquiring data. And what I'll leave you with is just a motion interpolation video of all of the data from 2012 to 2024 in both Cartesian and polar coordinates for you to enjoy. Thank you. Ready for any questions?
Thank you. It was super cool. Julian Girard from Space Telescope Science Institute. Those simple images are basically 30, 40 milliarc-second resolution. It's just mind-blowing. I was going to ask, do you have H-alpha, attempted H-alpha detection of the protoplanets?
I have not. And I don't know who has between MAG-AOX, ZIMPOL, and SKEX-AO. The data might exist somewhere, but I haven't looked at it.
Olivier Absil, Liège University. I was wondering whether you have seen any wavelength dependence in the structures in the disk, and whether this can bias your study in any way.
Yeah, I think there definitely are some structures you can see different across the wavelengths. What I'll point out here, something that I've found really interesting is if you look at the ZIMPOL data, for example, it's the highest angular resolution and also the bluest, the most visible. You get this really clean kind of ring structure, but if you compare that to our K-band, it's really hard to see here. There's like a plateau of data here. And so as we go redder, it seems like we're actually seeing that transition of smaller to larger grains through that pressure trap, even in the scattered light data. So what I'm trying to point out here is that we can see additional signal here at the redder wavelengths that we don't see at the bluer wavelengths. It's a bit easier to see on your screen than from the paper.
Yeah, actually, I wanted to come back to this because I think in another panel you showed, we can clearly see it's a double ring almost in the K-band data. And one of the other panels you showed, I think we can see clearly one of the early, here.
Yeah, so that's what I'm talking about. Instead of this this inner bit, you can actually see, and if you look at the radial dependence, this is the same separation as that ring, and this ring is actually much closer to the separation that we see in the millimeter emission, further kind of showing that we're seeing larger wavelengths and how they appear in this disk.
You can also see it in the GPI data.
Yeah.
I thought it was an artifact, to be honest.
Yeah, I mean, the Keras data also has some K-band in it. It's spectrally collapsed from J to K-band, but it's also showing that little outer plateau a bit.
I was interested, you mentioned you thought that some of the substructures you were seeing might be just PSF subtraction residuals.
Yeah.
How does that compare to epoch or wavelength? Oh, sorry. for folks online, sorry, folks. My question was, you know, you mentioned that some of the substructures you thought might be PSF subtraction residuals, and how does that compare between wavelengths or epochs?
So the idea here is, what I said was that this spiral wake here is not actually a spiral wake. That's just the outer ring being imaged through ASDI and seen in these residuals. In my data, I don't get something quite as clear as that. So what that feature is looking at in the outer ring is, it's kind of hard to see here, but it's this overdensity. If you can see the outer ring is a little bit dimmer here compared to here. So I think what we're seeing is in just a residual of the ring from here. For my analysis, when I look at the outer ring motion, I get, it's like negative 0.1 degrees plus or minus 1 degree per year, which means I can't tell if it's moving at all, really, but that's 2 sigma different than the velocity of the protoplanet candidate in the gap. And because of that, I mean, it's only 2.2 sigma, but it kind of shows that it's definitely not moving fast enough, but we're seeing a much different morphology here. It's not a little sharp edge, it's kind of this very broad, diffuse, bright structure that we're seeing over a quarter of the ring.
Yeah, thanks very much, and thanks for giving me chair's prerogative to go a few seconds over. Thanks very much for your nice results.